Okay, let's go ahead and start the class. Last week we talked about, we started chapter 3 of the book, which essentially means that we started talking about different types of pressure, stagnation and static pressure, different types of velocity measurements. And I think we stopped at the flow over a cylindrical surface, right? We just started talking about the flow over a cylindrical surface, but then we had to stop. So we are going to continue the discussion. We are going to talk about potential flow theory and elementary flows, and we'll go on from there. Okay, so let's go back to the flow over a cylinder. Let's say you have a cylinder, and we have flow passing over it like this. Okay, and we had the velocities. I gave you the velocities with respect to r and theta in the cylindrical coordinate system. 1 minus r squared over r2, v infinity cosine of theta, and v theta is negative 1 plus r squared r2, v infinity sine of theta. And just to make sure we are on the same page, v theta at any point is going to be the velocity that is tangent to the cylinder, or if you're far from the cylinder, velocity that is tangent to the circle enclosing the cylinder. And Vr is going to be the velocity normal to the surface. And eventually the goal is to calculate lift and drag for this type of flow over a cylinder. So how do you think we should go forward? We have the velocity distribution, Ver and V infinity, and we want to find lift and drag. What do you think we should do? Let's just start from lift and drag and just go back to velocity. Okay. What were the equations we had to calculate lift and drag? You remember the lift and drag were related to the integral of your pressure and friction, right, over the surface. That was the idea. Depending on the direction you are taking this integral, you would get lift or drag. So the goal here should be to get to pressure and friction distribution over the cylinder using the velocity distribution. Okay. Let's see if we can simplify this a little further. Do we have friction in this case? Exactly. The idea was we are mostly dealing with inviscid flow unless you are told otherwise. So we essentially have to find the pressure coefficient or pressure coefficient distribution or pressure distribution in a more general term on the surface of this cylinder, right? First step would be to find the velocity on the surface of the cylinder. So this is a cylinder of radius r, and we have the velocity distribution for the whole flow around the cylinder. Right? To find the pressure distribution or pressure coefficient distribution doesn't really matter. We should first find the velocity on the surface itself. Okay. How can we find, based on we have the distribution, how can we find the velocity on the surface? That's it, right? So for this r, which is going to be the distance of any point from the center of your cylinder, to find this velocity at the surface, we just have to say r is equals to r. So plug that in. If you plug it in here, we're going to get r squared, which is 1. 1 minus 1, 0. So Vr is going to be 0. For V theta, if we plug in r, it's going to be 1 plus 1, 2. So we are going to get a negative 2 V infinity sine of theta. So what does this mean? This means that on the surface, only velocity component is going to be V theta, which essentially means that on the surface, your velocity vector is always tangent to the surface. Okay? So on the surface itself, there is no component normal to the surface. The velocity is always going to stick to the surface and will be tangent to the surface. Since this is not an a viscous flow, the velocity on the surface itself is not zero, is non-zero. Velocity is going to be equal to negative 2 infinity sine of theta. Okay? So we have the velocity distribution at the surface, but before moving on, let's find the stagnation points, just as a practice. What are the stagnation points for this flow? Or let me back up a little bit. What are stagnation points in a flow from your fluid mechanics? Who remembers what stagnation points were? Velocity is 0. These are the points where the velocity is going to be 0. So velocity is 0 at any point. Those points are called stagnation points. Which is in line with the definition of stagnation pressure or stagnation properties. The idea was we bring down the velocity to 0 and the measure pressure. That pressure is going to be your stagnation pressure. So a stagnation point is where the velocity is 0, which means that the both components of velocity at any point have to be 0. Keep in mind that we are trying to find the stagnation points here for the flow, not just on the surface. So what are the points on which we are going to get velocity 0? Both velocities to be 0. Just look at these two equations and see if we can find the points which the velocity are 0. So these two velocities can be 0, where either this sine of theta and cosine or cosine of theta is 0. Yes. For VR, right? So for VR, when r squared, which is essentially when we are moving on the surface, VR is going to be 0. Is this the only point when VR is going to be 0? So what is the other point? When cosine theta is 0, in this direction, right? Okay. Is there any way? Let's look at the cosine theta 0. Is there any way V theta is 0 on those locations where cosine theta is 0? No, right? Because you have 1 plus, so this term is never going to be 0. And sine of theta is never 0, where cosine of theta is 0. So you have to work with the surface point, where r is equals to r. Okay? So a stagnation point, your r is always equal to r, in which Vr is going to be 0. But at which point V theta is going to be 0? Pi, right? Exactly. Where sine of theta is 0, which means that your theta is going to be 0 and pi. Right? So there are two stagnation points in this type of flow. One is going to be at this location, and the other one is going to be at this location. And in general, when you're dealing with flows over cylinders, this is going to be your sign convention. This is going to be positive theta, and this is going to be positive r. But this is a sign convention. So we start from 0 here, then rotate to pi over here. Okay, we have the stagnation points. It was a side thing to find the stagnation point. But we're going to use these stagnation points later on. Okay, so let's see if we can get this velocity distribution on the surface and find the pressure coefficient. What was the definition of this pressure coefficient? Who remembers? How did we define the pressure coefficient? No one? I always ask this question, and we always wait for 30 seconds, someone says it. So it's pressure or pressure difference, right? P minus P infinity divided by Q infinity. In general, all of these coefficients are divided by Q infinity, right? Force divided by Q infinity. So your force here is P divided by Q infinity S. Your force here is P multiplied by S, which we don't have that. And the two S's will cancel out. And instead of pressure, we are going to use the pressure difference. So how is this related to velocity? We already know that this part is 1/2 rho v squared. Okay? But what can we say about the numerator? How is the numerator related to velocity? Any velocity? Yes. We are in the incompressible flow. So that's for the compressible, right? And my question is, how would you relate pressure or pressure difference to velocity? Bernoulli's, okay? So let's say you want to write Bernoulli's for here, this point on the surface. So this point here, where we have infinity properties, P infinity, V infinity, and this point here, where we have P and V for pressure, a random pressure, a random velocity, which is consistent with the definition. If you apply Bernoulli's, you're going to get P plus 1/2 rho V squared equals to P infinity plus 1/2 rho V infinity squared, right? Okay, so P minus P infinity is going to be equal to 1/2 rho V infinity squared minus V squared. Does this make sense? So let's substitute that here. In the numerator, we're going to get 1/2 rho v infinity squared minus v squared divided by 1/2 rho v infinity squared. 1/2 rows will cancel out, and we can essentially simplify this to 1 minus v divided by v infinity squared. So as long as we have the velocity field or velocity distribution on a surface, we will be able to find the pressure coefficient. So for this, and this is true for any type of inviscid incompressible flow, right? As long as you can apply the Bernoullis between any points, any 2 points, right? But for this specific flow where we have the v infinity, something that I may need to mention, the velocity vector is VR ER, right, plus v theta E theta. That's the cylindrical coordinate system, but VR is 0, so we are only going to get v theta E theta. So your velocity vector is essentially equals to v theta. So let's plug that in. We're going to get 1 minus negative 2 v infinity sine theta, right, divided by v infinity to the power 2. What does it mean for the pressure coefficient? It essentially means that your pressure coefficient, the distribution of the pressure coefficient, pressure coefficient profile is going to be equal to 1 plus 4 sine squared theta. Okay. Is there any questions? Let me ask you this before moving on. What is the maximum velocity on the surface of the cylinder? And where do we get it?
The max velocity at the pi over 2 and 3 pi over 2.
Exactly. So VR is going to be 0. The velocity is only v theta. And the max velocity will be where sine of theta is 1, which essentially means that your max velocity is going to be to infinity, right? In this direction. On these 2 points. Okay, so let's see. And this is 1 minus. I'm sorry, guys. 1 minus 4 sine of theta. So this minus sign goes to the power 2, becomes a positive. We are not going to lose that minus sign. Let's see. How would the distribution of pressure coefficient on this cylinder would look like? Okay. At theta equals to 0 and pi, our stagnation points, what would be the pressure coefficient? This is the formula, right? 0 and pi, what would we get for pressure coefficient? 1. Okay. Maximum velocity, pi over 2, 3 pi over 2. What would be pressure coefficient? -3. Exactly. So if you want to have a graph of how CP changes with theta at theta 0, we're going to get 1. Then it will go down to -3, go back up to 1. And the same will be true if you move on the other side. So essentially go back from pi to 0, right? You can continue like this. So this is how pressure changes, or pressure coefficient changes with respect to location on the surface of the cylinder. Any questions so far? No. Okay. So let's do what we were supposed to do, what we wanted to do. Let's find the drag coefficient here, since we are dealing with pressure coefficient and lift coefficient. We had the integral formulas for the normal and actual force coefficient. In this case, the angle of attack, it's a cylinder, so it doesn't really matter what is the angle of attack, right? Your normal force is always going to be the lift force, right? And your actual force is always going to be the drag force. So what were the equations? What were the those integral equations we had for Cn and Ca? I assume no one remembers, because these are very long equations. So we had the integral of pressure coefficient for lift, that's the x, plus the integral of 1 over c, leading edge 0 to c, cf dy dx minus cf, that's cf and upper, right? Cf and lower, dy dx dx. Okay. And then for CD, or the drag coefficient, we had CPU dy dx, or is it dx dy? Dy dx minus CPL dy dx dx plus 1 over c integral of the frictions dx. Okay, so what can we say about the friction coefficient in these equations? Zero. Okay, because inviscid, so this will go away, which is good news. We can actually simplify this because it's a very cylinder as well. CD is going to be equal to 1 over c integral of CPU minus CPL dy. Okay, and we already have the equation for CL. But what is the physical representations of these equations here? Just to make sure that we are clear. We are taking the integral for, let's do CD first. We are taking the integral of, essentially, integral of CPU dy minus CPL dy. Or front and back. Doesn't really matter. So we are calculating the pressure force on this part of the cylinder, and then on this part of the cylinder, and we are just subtracting these pressure forces, which supposedly is going to give us the drag, right? It's going to give us the force in this direction. We are doing the same thing for lift. The only difference is that we are calculating the pressure force on this surface and then subtracting it from the pressure force on this surface. Does this make sense? Okay. Okay, so let's see. What is the pressure coefficient on the upper surface? What is the pressure coefficient on the upper surface? It's going to be 1 minus 4 sine squared of theta, right? What is the pressure coefficient on the lower surface? Same thing, same equation, right? So what does it mean for the integral? For both integrals? We're going to get 0, right? And the same distribution of pressure coefficient, you're going to get, let me use a different color. You're going to get 0 for drag and 0 for lift. Because of the fact that we are getting 0 lift, this type of flow over cylinder, over a stationary cylinder, is called the non-lifting flows, because it doesn't generate lift. Essentially, pressure distribution on top and bottom are going to be equal. Okay? But how can we explain the fact that drag is 0 here? Does this make any sense? No, why not? So we are essentially pushing the cylinder, right? There is a drag force. We can see that there will definitely be a drag force. This doesn't make any sense. So what does this mean? This essentially means that the implicit assumption is definitely wrong here, right? Because we are calculating 0, at least for the drag force. We are calculating the 0 drag. This phenomena that the implicit assumption is wrong, because at the time they didn't know anything about viscous flows, is called the D'Alembert paradox. This guy, I think, is a French physicist, was a French physicist in the late 18th century. And he was the first person to observe this paradox, right? That you are getting 0 drag, which obviously you shouldn't, because you are pushing the cylinder, right? You should get some drag, right? And essentially understood that the implicit assumption does not give you the complete picture, the full picture. You have to include something else in your analysis. But to understand this better, we essentially need to have a closer look of what is mainly generating, is responsible for the drag here. So look at the flow. Let's magnify this part. How would the real velocity distribution look like? The idea was you will have a formation of something called the Barney layer, which essentially means that your velocity is going to start from 0, then it will increase, right? We have talked about boundary layers, and you have seen them in your heat transfer course for sure. But we didn't include these in our analysis here. We didn't include the boundary layers. We decided that the flow on the wall is going to be non-zero. We're going to have a finite velocity, which is not the case if you are having no slip condition. We have talked about these conditions a little bit. So one of the reasons, or the reason that we don't really see any drag here is because we are removing a very important physical phenomena here. And this is one of the few cases in which the implicit assumption is going to give you this inaccurate of a result. Right? In the other cases, we won't really see this inaccuracy. We can like get a good assumption, get a good estimation of drag force in some other cases. Okay. We're going to come back to boundary layer analysis and their effects on friction drag, pressure drag, all of those things. Later in the chapter, at the end of this chapter, we will have detailed analysis here. But let's move on. So here, for this type of flow, this is the flow over the cylinder, the non-lifting flow over a cylinder, we assumed the velocity distribution was given to us, right? Which doesn't really happen in the real world. Yeah. What should we do then? How can we find the velocity distribution? We cannot just put flow meters everywhere in this flow and come up with the velocity, find the velocity distribution experimentally, because when you put a flow meter in the flow, you are disturbing the flow. So experimentally, it is a very hard thing to do to find the velocity distribution. We have to have some sort of an analytical methodology to be able to have an idea at least on what the velocity distribution looks like over at least simple geometries. This is where potential flow theory comes in. If you recall, we talked about stream functions. Psi and velocity potential phi. Okay. We define the velocity potential as essentially this. Velocity distribution is going to be the gradient of the velocity potential. Yeah. But how did we define the stream functions? What was the equations for stream functions? Or how did they relate to velocity in a Cartesian coordinate system? Who remembers? Or you can go back to your notes just to refresh your memories. Stream functions, how did we calculate velocity components in a Cartesian coordinate system using the stream function? U equals to partial psi, partial y, okay? Partial psi, partial x, right? Okay. This is how we define exactly. This is how we define a stream function, and this is how we define velocity potential. We are dealing with inviscid incompressible flows. So if you recall, the continuity equation was this. The divergence of velocity is 0. Okay. So let's do velocity potential. You're going to get, if you plug, instead of velocity, if you put velocity potential, we are going to get del phi is going to be 0. This del can be replaced with the Laplacian operator, del squared. Del squared. Who knows about the Laplacian operator? One person. Two people. That's all right. So that's where it comes from. Del dot del is going to give you del squared or the Laplacian operator. It is called, if you cannot hear me very well, it's called Laplacian. So we are going to say in an inviscid incompressible flow, the Laplacian of velocity potential is 0. Okay. We are going to use this to build up the potential flow theory. So just bear with me. We're going to get there. We can also prove this for an irrotational flow for the stream function, that the Laplacian of the stream function is also 0 for an irrotational flow. What was the main characteristics of an irrotational flow? Does anybody remember? Kerr-Law velocity is 0. So del cross V is 0. And this is where you're going to get a bonus point. Just use these definitions in a Cartesian coordinate system. And the fact that for an irrotational flow, Kerr-Law velocity is 0, to prove that for this irrotational flow, Laplacian of the stream function is 0. Okay? So this is the bonus point. Prove the Laplacian of the stream function is 0 for an irrotational flow. I usually get a lot of submissions from the graduate students for the bonus points, but I don't get any, or not that many, from the undergrads. And I should say undergrads are the ones who need the bonus points more. You can try, you can copy it from the book, you can do whatever you want to do, right? You can talk to your graduate student classmates and get the answer for it and just submit it. These are free points that you can gather, right? And you have to keep in mind that I don't curve the grade. There is no way that I curve the grades. The only way you can earn points is through bonus points, right? So I usually say this in the beginning of the class, but I think I didn't say that. So yeah, make sure to use this opportunity. Okay, so we have for an irrotational incompressible flow, we understand the Laplacian operator or the Laplacian of the stream function or the velocity potential, both of them is 0. But why is this important? Why do we need it? Where are we going to use this? It goes back to the definition of this type of function. Laplacian of any function is 0. If this is true, what's going to happen is that you can create new, let's say there are solutions to this function, f1, f2, f3, right? Then the summation of these solutions is going to be an acceptable solution as well. What does this mean? It means that if we can have very elementary flows for which we can find the psi and phi, velocity potential, and the stream function, then we can create more complex flows by just adding the stream function for one flow plus another flow. Does this make any sense? When you have the solutions, when you have the stream functions, velocity potential for a simple flow, you can create two simple flows. You can create a more complex flow by just adding the two flow. And to find the velocity distribution, you add the two sides or two phi's, and you can find the velocity distribution for the more complex flow. Okay. To give an example, so you can understand better, and we're gonna introduce the elementary flows we're gonna use, like this flow, uniform flow. Velocity doesn't change. There is no change in direction. There is no nothing, right? What is the velocity distribution for this? U equals to V infinity, right? And we can find also the velocity potential for this based on this definition. Velocity is, in this case, it's a one-dimensional flow, so velocity is going to be the gradient, the derivative of phi with respect to x, right? For this uniform flow case, which means that your velocity potential is going to be V infinity multiplied by x. You just have to take the integral of the velocity, right? Does this make sense? Does this make any sense at all? Or is this confusing? Is it confusing? Yes. Okay. Which part? Just tell me if you understand the uniform flow part. Okay. And do you understand how we get the velocity potential? Based on the definition. Okay. Do we all understand this? Okay. That's good. And then I'm going to come back to this, and I'm just giving you an example. And then we have this type of flow, which is called a source flow. I think this was part of your homework as well, right? This type of flow. Or the vortex flow was part of your homework. One of these were the vortex flow. Doesn't really matter. We can find we will have the velocity. We can find the velocity distribution and the velocity potential for this as well. I'm going to tell you later on that what is the velocity distribution and potential for that. And then using these two type of flows, we can create a more complex flow. How do we do that? Let's just add these two together. So there is this uniform flow coming here, and we have the source flow here, right? In one direction. What is going to happen when these two flows meet each other? You're going to get a stagnation point, right? Uniform flow. When the uniform flow gets to this part, is going to tilt your source flow, right? That's the interaction of two vectors, essentially. And you're going to get something like this. Eventually, your uniform flow, I'm just adding these two vector fields. And let me know if you don't understand this. It's going to look like this. Okay? Does this make sense? I'm just adding the two flows. So essentially, you can create a line from the stagnation point, and you're going to get a velocity vector on the stagnation point. So if you add these two type of flows, this is what you're going to get, right? If we remove the inner parts by just adding a condition, R is always bigger than this radius, right? They're essentially going to remove the source flow parts. What does this look like? This looks like flow over an airport, right? So we're essentially using two simpler flows. We are going to create a more complex flow. And then if you have the velocity potential for these two, we're going to find the velocity potential for this more complex flow by just adding them. Velocity potential of this, phi1, plus the velocity potential of this. Yes?
And the reason that we can add them together is because the velocity of both of them is equal to 0.
That, yes, that's one of that's the main characteristics of this type of function. Harmonic functions, yeah. Exactly. Did it become a little more clear? Okay. So essentially, as long as we can come up with a couple of elementary flows, what we call elementary flows, like these two, we will be able to build more complex flows. The only thing we need is to find the velocity potential and the stream function for those elementary flows. Then we can create more complex, whatever you want, whatever you need, essentially. Does this make sense? Is this clear? Okay, so let's talk about the elementary flows then. And this is something that you can always have with you, that elementary flows and their velocity potential and the stream function. Yeah. The first elementary flow is the simplest type of flow, is a uniform flow in which all of the streamlines are moving at a velocity v infinity. Velocity function for this is going to be v infinity multiplied by x, and the velocity as the stream function is going to be v infinity multiplied by y, for a very simple reason. Stream function is defined as partial u partial y, right? Your u is essentially v, so u is going to be the integral of psi partial y, right? We have the v infinity, we have the integral of psi partial y, right? What am I talking? Yeah, and then you just take the integral with respect to y, you're going to end up with v infinity y. The same thing we did for the velocity potential. Since we have the other types of elementary flows are mostly like this, it is not a bad idea to have the cylindrical form of this type of flow, which is going to be v infinity r cosine of theta, v infinity r sine of theta. We have the potential, we have the velocity potential, we have the stream function. We should be able to find the distribution, velocity distribution, right? The velocity profile. Okay. The other type of elementary flow is called the source or sink flow. When the velocity vectors are getting away from your source, this is called the source flow. When the velocity vectors look like this, this is called the sink flow. But these two are essentially the same flows. The only difference is the velocity direction. Velocity direction is changed. Velocity is going to be in the opposite direction. What does these two types of flow remind you of? Yes. No. But what type of flows? Like in real world, what does these two remind you of? We have another flow called the vortex flow, but this is vortex. You're gonna get some rotation, right? We don't have any rotation. This is a sink or a source that is moving at a very, very, very slow velocity, right? This is how it's going to look like your sink, your bathroom sink. If the water goes on at a very, very slow velocity, right, then you won't see the rotation that much. If you are at the equator, this is how it's going to look like, which doesn't really happen in the real world. But so, what is the potential? And a stream function for this type of flow, velocity potential is lambda over 2 pi natural log of r. Lambda is the strength of the source or sink. Lambda, a strength of the source or sink. A strength. And it's usually given to you, or you can like determine that pretty easily. And the stream function is going to look like this. Lambda divided by 2 pi multiplied by theta. Okay, so based on these two, based on the question,
And what is n at the end of the?
this
No.
natural log of r, ln r. Natural. I've never learned cursive in a school, but for whatever reason, I do write cursive. So natural log of r. Okay. So who can tell me what is VR and V theta based on what you're seeing here? You have the potential, you have the stream function, you can use either of those to get the velocity, right? What is VR and V theta? To find the VR, how do we find this VR? Using your potential. Derivative of it with respect, using the potential derivative of potential with respect to R is going to give you VR, right? Okay, so what does it mean? Your VR is going to be equal to lambda. What is the derivative of natural log of R with respect to R? 1 over R, that's it. So your VR is going to be lambda divided by 2 pi R. What does it mean? Your velocity is going to become smaller and smaller as you go further and further away from your source, right? So there will be a decay and source, your source strength, your source velocity. Well, what can we say about V theta? You have to take the derivative with respect to theta, right? What is the derivative of this potential with respect to theta? 0. So for a source, as you can say from the picture, as you can say from how they are defined, for a source flow, we are only moving in the R direction. There is no movement in the theta direction. The other type of elementary flow is called the vortex flow, as one of your friends mentioned. Who mentioned the vortex flow? It was you, right? What was your name? Wyatt, as Wyatt mentioned. So we're going to get these rotations around a center. Your phi for a vortex flow is going to be equal to what? Negative gamma divided by 2 pi theta, and your psi is going to be equal to gamma divided by 2 pi natural log of r. So if you compare these two, you can see that they are essentially the other way around. Your velocity potential is the stream function for the vortex flow. Velocity potential of the sink or source flow is the stream function for the vortex flow. And the stream function for the source or sink flow is the velocity potential for your vortex flow. So what is VR and V theta here? Based on what I just said, that the velocity potential and psi are reversed compared to the source and sink flow, what can we say about VR and V theta? VR is 0, exactly. What is V theta? You can use either of these to find V theta. What was the formula we had for V theta? What was it? Let's go for phi here. How can we find V theta using velocity potential? What was the formula? Does anyone remember? Or you can go back to your notes if you have them. Negative partial psi by partial r. Exactly. That's for psi. So for psi, V theta using psi is going to be negative partial psi partial r. Thank you. And for if you want to use velocity potential, it will be 1 over r partial phi partial theta. Both of them will give you the same result eventually. V theta for a vortex flow is going to be equal to negative gamma over 2 pi r. Okay? There is only one more elementary flow, and that is called the Doplet flow. Doplet flow is going to look like essentially a combination of two vortexes. This is called the doublet flow. And the strength of this doublet is called kappa. Your phi is going to be equal to kappa divided by 2 pi cosine of theta divided by r. And your psi is going to be equal to negative kappa divided by 2 pi sine of theta divided by r. So based on these two formulations, you can see that we are going to have both VR and V theta for the doublet flow. And this is the center of your doublet. Okay. So we essentially have 4 main types of elementary flows. We can combine these 4 together to get to more complex types of flow. We talked about one of the combinations that we saw. Okay. There are other combinations that we can do as well. Just to give you some examples. I don't need to actually wipe anything. Okay. So other combinations. Let's talk about the flow over this. Let's actually talk about this. This is something that we just did, right? Flow over a cylinder. We just analyzed, right? We talked about the D'Alembert paradox and all of those things. This is an inviscid incompressible irrotational flow, all of those things, which essentially means that for this type of flow, the Laplacian of your velocity potential and Laplacian of stream function is 0. What does it mean? It essentially means that we can use simpler flows to build this more complex flow. So, what do you think? Which types of flow can we use here? or should be used here to build up this type of flow. Flow past the cylinder. We are going to get uniform flow, of course. Thank you, Trevor, right? We're going to get uniform flow. That's one of them. But for the second one, Trevor said vortex flow. Let's do that. Let's see what we are going to get. If we had, the idea was here, the velocity here and here for a flow past the cylinder are the same, right? We are going to have the same velocities. If we have the vortex flow, and with the center of vortex here, we are not going to get the same velocities on top and bottom, because on the bottom, you're adding these two velocity vectors. On the top, you are subtracting, right? So it cannot be vortex flow. But what do you think? What is it then? If not vortex flow, which flow? Source flow gave us something that resembled an airfoil, right? Which was a semi-infinite body, right? Because you wouldn't get this type, you won't get the stagnation point at the end of your cylinder, right? Because at this part, your velocities are in the same direction. You're essentially adding to the velocity. So we want to get a type of elementary flow that's going to give us a stagnation points here, same velocities here. Doublet flow, that will be the only other option, right? Which is true. So if you have a doublet flow, you are going to get flow past the cylinder. So for a uniform flow, what was the potential? The infinity r sine of theta, right? That was the potential for cosine of theta, not sine. Did I say sine of theta? I don't remember. So if I said for potential it's the infinity r sine of theta, just make sure to correct it to cosine of theta. And your psi is the infinity r sine of theta. Okay, just make sure. I think I said the wrong psi, sine, and cosine here. I gave you if it's the wrong one, make sure to correct it in your notes. But you will get the correct one in your book anyways. So what is, and we also have the psi and phi for the doublet flow. We essentially, to get the velocity profile here, we can find the psi of this type of flow. Let's call it the cylinder flow. Psi of C is going to be equal to psi of doublet plus psi of uniform flow. Psi of uniform flow is the infinity r sine of theta. And for the doublet flow, we have negative k or kappa 2 pi sine of theta divided by r. Based on this, we will be able to find, or based on the velocity, we can do the same thing for the velocity potential. Okay, based on these two, we can find Vr and V theta for flow past a cylinder. Okay. The only thing you really need to know here is the strength of your kappa, which needs to be determined, which you should determine that a strength of kappa in a way that gives you zeros here, right? You have 4 boundaries essentially. 0 here, 2 V infinity is here on the surface of the cylinder, right? Yes. the first thing you need to do is to find the VR and V theta as a function of kappa, right? And then you know that the velocity is going to be 0 and 0 here and here. Then you can determine kappa, right? You can find a value or a range of values for kappa. Okay. So what is the let's do another example, which is going to be the example we are going to focus on in the next lecture. Flow past a rotating cylinder. So we have a cylinder that is rotating around the center, and there is flow passing over it. How do you think the flow would look like? There is flow over a rotating cylinder. How do you think the flow would look like? Let's do the direction of rotation in this. This is the uniform flow plus the vortex flow that we saw, right? Which essentially means that we are moving the stagnation points, right? Because the velocity at one side, as top of it, is going to be higher because it's being added to the uniform flow by the uniform flow. And velocity on the bottom side, bottom surface, at this like 2 pi over 3, right? At 270 degrees is going to be less because it is being subtracted from the uniform flow velocity, right? Okay, which essentially means that your stagnation points for this specific flow are going to move down. They're actually going to look like this, right? Yeah. So this is what your flow will look like. It is not that hard to understand. You have lower velocity here, higher velocity here, right? And they are moving in the opposite direction. You will definitely, not definitely, but there is a situation in which you can get 0 velocity on the surface because you are moving at a high velocity to a low velocity, right? Magnitude of velocity is going to be lower on this surface, which means that 0 velocity is going to be closer to this surface. Okay, we are going to talk about this type of flow in more detail because this is the first type of lifting flow we are going to analyze essentially. But this is again an example of your Laplacian 0, which means that we can break it down to simpler flows. Those simpler flows are going to be uniform flow and vortex flow. Yes. You are pointing to the D'Alembert paradox, right? We can remove the inverted assumptions, right, and do the analysis, right? But the reason this rotation is important is because of the viscosity, right? So that's a very good observation. Thank you for that. So if we do not include the inverted assumption, or if we do not include viscosity, which means that we assume that this is inviscid, we will be able to analyze this, right, and get a drag coefficient. But the reason we have this type of flow is because of viscosity. So we are neglecting a very important phenomena that is the main reason, underlying reason behind the existence of this type of flow, but doesn't contribute that much to drag force. Does this make sense? So neglecting that in the analysis, we cannot neglect it in the real world. We are just neglecting in the analysis. Will give us a good estimation of the drag force as long as we can find the distribution, pressure distribution, right? But friction is the underlying reason that this type of flow exists. So what Paul, right? What Paul is saying, if you didn't hear him, or if you don't understand, is that if we are assuming the friction doesn't exist, it doesn't really matter whether the cylinder is rotating or not, right? There is no way a rotating cylinder can tell the flow that it is rotating if friction is not there, right? The only means a rotating cylinder can tell the flow that I'm rotating is through friction, right? So if a friction does not exist, it doesn't really matter. It will be just the same as the flow past a stationary cylinder. So the reason flow sees the friction, sees the rotation, is because of friction. But the share of friction, or the friction coefficient, or friction drag in the total drag force is as small as minimal, right? So we can, in the analysis, we can neglect that in this type of flow, not every type of flow, in this specific type of flow, right? Does this make sense? Yes, no? I have a couple of yeses, one so-so, one so-so. Okay, so-so is good enough. So-so is good enough for me. Okay, I guess that's it for today. Thank you for coming to the class. And I'm working on the Fluent tutorial. It will be posted sometime this week for sure. That's for sure. I will also post the Python tutorial for the finite difference analysis that we talked about. The finite difference analysis will be part of your homework, that's for sure. It may be part of your exam as well, but that's the mathematical calculations. So finite difference analysis, numerical simulations. We talked about numerical. I don't know if you were in that class or not. Okay. Yeah. So it may be part of the exam, but that it will definitely be one of the easier questions on the exam.